Right. So last class, I gave a bit of a introduction, let's say, to gravitational fields. And what we started the conversation with was what is a gravitational field in essence? And we described the field as saying it's a region of space where any object experiences a force. That is what we explained gravitational field as. And today, what we are going to get in depth with, we still did introduce this law last class. That was the law of gravitation, where we formulated a formula for finding out the force due to gravitational fields. And that formula is given by this. So we formulated a formula and we found out that the final formula comes out to be uh, F is equals to Gmm by R square. And this formula tells us that if there's any object in the vicinity of another object that experiences a force, and that force can be given by this specific formula where we have the gravitational constant being multiplied with two masses divided by their separation squared. So this is the formula we understood. And when does this force really apply? When do we really see this force? Let's say I have essentially an object over here, and I have another object over here. Okay. Now, what I want to show to you guys using the formula we sort of explained by the law of gravitation, which says your force or the gravitational force between two point masses is proportional to the product of the masses and inversely proportional to the square of their separation. This is a set of proportionality that is presented to us that if we combine everything, so one of the information given is the gravitational force is proportional to the product of 2 point masses. So that says my gravitational force must be proportional to the product of both my masses which are interacting. If I have an object over here and an object over here, both of these will have gravitational field. They're separate one. Due to having that, they will come and interact no matter how far they are, no matter how far of an r separation they are at, doesn't matter. However far they are, they will have some sort of an interaction. And hence they'll apply a force on each other. And that force is being told to us that it must be proportional to the product of both of their individual masses. So the small mass m1 and the big mass m2. Okay, so that's one of the proportionality given to us. What's the other one? It says it is inversely proportional to the square of their separation. So if my object over here, m1, is standing over here, then my m2, which is this far away, their separation is inversely proportional, separation squared. So it says my force, right? This is one proportionality given to us according to this law. And the other proportionality given to us is F is inversely proportional to the square of their separation. So R squared, inversely proportional. This is called inversely proportional. So if R increases, the F will decrease as a square of it. Okay. So if R increases, F decreases in square proportions of R. Okay. So essentially, these two proportionalities are given to us. And when we combine these two, what happens is we can say F is proportional to the product of two masses and inversely proportional to the separation that the two masses are at. No, not much. I'm still repeating the last class content, the end of last class content. So you haven't missed much. So again, yes, over here, what I've done is I joined the two proportionalities that is given as according to the law of gravitation. That is all I've done. Now what do we do? Now this is a proportionality. This is not an equation. This, my friend, is a proportionality, not an equation. So when scientists found out that this is the relation of force, mass, and separation, they started plotting things. They did what? They plotted things. What they did was they were, let's say, plotting the force that they experimentally found out against, let's say, um, they were probably changing the mass, m2, or they were changing the separation. One variable they changed. Let's say they're changing the mass, m2, and this remained constant, let's say, m1 and r2, sorry, r square. So they kept some of the variables constant, and this being a dependent variable changed according to how you changed m2, right? So m2, let's say, is the independent variable, and I change m2, and they plotted how the force increases. What they saw is it produces a straight line, and the gradient of this straight line is going to be Gm₁ by r square. Now notice m1 and r square we didn't change as well, which is why it's a part of the gradient. But you remove m1 and r square, what do you have? A constant. So what they were trying to do experimentally is they were trying to find out the gravitational constant. Now m1 and the separation r square, you know, so you can just equate it to an equation saying, let's say, Gm1 by r square is my whatever gradient they find out. So my gradient over here, experimentally found out, my friend. And you know m1 and you know r square, and you make g the subject, and that's how they found out gravitational constant experimentally. So they plotted two things, right? They plotted two things. They changed, let's say, the mass, either of the mass, whatever they wish to change, and they plotted the thing, and they found out the gradient, and that's how they found out the constant g, right? What is the point of saying that? It's just that to feed your curiosity. If you guys are confused as to how did we even find g, or how did we come across this equation, just to talk about that, I explained it. Now, ultimately, when you remove this proportionality sign, you know you have to introduce a constant. You have to introduce what? Constant. And that is what g is. Ultimately, when you remove that proportionality sign, you can say f is now equals to this constant g times product of both the mass divided by separation squared. Fair enough. As simple as that. Okay. Now, other thing that I mentioned last class is where do you measure the separation from? The separation between two masses, you don't measure from the surface. No, 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 no. If you have a graph, right? If I have a graph paper over here and I have a circle over here, what is the position of the circle? It's a 1, 2, 3, right? 1, 2, 3, 1, 2, 3. What's the position of this circle? Will you consider this to be the position of the circle? This? No, 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 no. You always consider the center of the circle as my indicator of where my circle is situated. Doesn't matter how big it is. It could be this big. What is the position of this big of a circle? You make the center the identifier of where the circle is, right? Now, hence, the position of this is 2, 2. However, in real life, well, that is not enough of a reason to say, well, just because it's simple geometrically, it's easier on the eye and it's easier to find out. That's why I've considered the center to be the position. Well, that's not enough of a reason to consider this center position to the as the position of a sphere, as a position of an object. Now, this approximation that my separation should be always considered from one center to another, this is called an approximation. This is not exactly definite. Why do I say that? This approximation that I should consider the position from the center of a circle comes from the logic that we can consider all of the mass of m1 to be concentrated over here at the center. Why do we say that? Understand very carefully. Sure, I mean, geometrically it also makes sense, but there's a deeper reason over here. There's a deeper reason over here. When you draw, let's say this is a completely uniform you know what uniform means. The mass inside this sphere is evenly distributed and it's an even sphere. So it does not have any sort of anything inscribed on it, nothing plucked out, even distribution of mass. Consider all of those things. Now draw field lines on it. Radial lines, the field lines, right? The radial lines, the field lines. When you do that, my friend, what happens is when you extend the lines, right? Sorry, when you extend the lines, you notice them to meet, you notice for them to meet right at the center. So field lines, all the field lines, no matter where you draw it, one thing you always notice, they seem to meet at one point. What is this point? This is the center of the circle. This is where we consider the center of the sphere to be. So if this is Earth, and we assume Earth to be spherical and of uniform mass, then the exact center of the Earth is where we can calculate things from. We can calculate the gravitational field from, the gravitational force from. The reason we can do that, the reason we can do that is because the radial lines, the gravitational field lines seem to all meet at this one point, which is why we can make this approximation that okay, my distance should always be counted from one center to another center. Okay, and I will again talk about this point mass approximation a bit later, I guess, right now. But in essence, that's why we consider the distance right from the center of a circle. Now what happens if this sphere is not uniform? It's a bit of a, like, let's say our Earth, it's not uniform, it's not completely spherical. What happens then? What really happens then is we still consider measurement from the center of the circle. We always consider the geometric center to be the center of gravity. Why do we do that? Because when we're measuring with respect to Earth, the distances we measure are so massive that it doesn't really matter where you count the center from. Let's say, to add perspective to what I've just said, if this is the center, the other possible center, let's say, is over here or here or here or here. Fair enough. Fair enough. But when I'm measuring the distance, I'm considering between Earth and some other planet really far away. So in that case, my planet is probably over here. So now notice R. How far is R? How far is R? It's really far away. Okay. Now, it does not matter where you consider the center to be. It does not matter. Why? Because the error, you have learned about physical in physical quantities, error. So over here, the margin of error is so little. Doesn't matter where you consider the center to be. So better to consider the geometric center and assume that Earth is a perfect sphere. Assume Earth is a perfect sphere and consider the center to be the geometric center. This is the geometric center. Doesn't matter how uniformly mass is distributed, because the distances I'm calculating with is so massive that the error becomes very little and it is of no substance to me. Now, if I'm talking about, let's say, satellite, yeah, then it matters because the distance I'm covering, now the error in my answer is going to be quite big. So I now need to calculate with respect to the accurate position of Earth's center. So if I have to find out the force on satellite, I should respect where the absolute center of gravity is for Earth. And that you calculate a bit differently. You don't study it over here. You study extended bodies and you find out using calculus where the absolute center of gravity is when you have non-uniform object or extended bodies like this. This is not a sphere. And if you assume the center of gravity is over here, no, 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 no. If there's a mass over here and there's a mass over here, this cube of a shape, you can't just say this geometric center is the center of gravity. Nope, nope, nope. The center of gravity over here between this interaction is not going to be this center. Because look, this part will attract M1 very strongly. So the closer end of the closer end of this bar will attract M1 very strongly, whereas the far end will attract M1 very little in comparison. And how little? By a margin of square. by a margin of square. So the distance,
Sir,
the
could you repeat that?
position, sorry,
Sir, could you repeat that again? Like the point mass attraction, that part
in case of extended bodies or in case of normal spheres.
in normal spheres.
So in normal spheres, we always consider that the center of the geometric center of the sphere is from where we start counting the separation between two objects. So we assume that all of the gravitational field is, or the force comes from this one point, which is called the point mass approximation. We forget that this mass has a radius when doing the calculation. We say all of the mass is concentrated to this point. Why do we say that? Draw a bunch of radial lines. What are these lines called? Radial lines. And if you extend them, all the field lines seem to meet at one point, this point. This is the geometric center of the circle. And this is where we assume all of the gravitational properties to be held in. This is where we consider, this is where we start measuring the separation from. So if I have a mass over here, this center is from where we consider the start of separation from. Why do we do that? Again, all the gravitational field lines seem to meet over there. So it seems like, okay, that is essentially from where we start measuring the distance. Okay.
Okay, sir, but in the syllabus it says we should understand that for a point outside a uniform sphere, the mass of the sphere may be considered to be a point mass at its center.
Yes.
So what do
Yes.
they mean for a point outside a uniform sphere? Like what do they mean by that?
So this is essentially what I explained. So what they're saying is for point outside the sphere, what really happens is when you draw the radial lines, all of them seem to meet at one point, which is why this assumption that all of the mass is concentrated at one point is valid. Because when we have the field lines coming in, this sphere, when it has its own perfect sphere, right, uniformly distributed, all of these seem to meet at this one point so far away from outside the object, essentially all the mass is in this one point with respect to where the gravitational fields are meeting. Okay, so that is the point mass approximation. Now, the other thing over here to include that the syllabus must also ask you to remember is even if my sphere is not perfect, even if my sphere is not perfect, from large distances, I can consider this sphere to be a perfect sphere. I can consider the point mass approximation, even if the sphere is not perfect. Why? Because at large distances, it does not matter. At very large distances, even if this body is ununiform, the margin of error becomes very little. Because compared to these deviations of distances, that is, of the center of gravity, notice what the distance of my separation is. So let's say there's a planet over here, planet G, and there's planet M1 over here. Now notice the distance between them. Now when I calculate and put this R in, right? So let's say I'm considering the R between, let's say, this point or let's say this point. What is this difference? What is this delta? This delta is very little. Doesn't matter where I consider the center to be in case of large separation of distance between two planets. In that case, the error cost is very little, which is why the point mass approximation for non-uniform bodies, like as of Earth, even in large distances calculated, is valid. You can do the point mass approximation and say the geometric center is where all the mass is, even though it might not be, even though the center of gravity might be, let's say, a bit deviated, and let's say, okay, over here, because the mass distribution is uneven. Even then, it's okay. Because what is the error over here? Very little of a distance change. So that's why your point mass approximation is valid. Do we get the point?
All right, thank you.
Yeah. So there are two things. One is why we can do point mass approximation, and the reason for that is draw a bunch of gravitational field lines, and what you see is all of them indicate to the center, geometric center. The second thing is even for non-uniform bodies. So over here, if you take a screenshot, even for non-uniform bodies, what happens is at large distances calculated, if we calculate force between two objects at very, very large distances, the distance is so much that the error in finding where the center of gravity is for any object is invalid. It doesn't really matter because that difference inside the object's body in distance doesn't really matter because the error caused by that is very little. Okay, in short, in real calculations, they're going to find the center of gravity and then do the calculation. But for us, it's valid. Why? The error is little. So it's because of that little error that we can overlook where the actual center is, and we assume or approximate with point mass approximation. Okay. In case of extended bodies, it's a bit different. In case of extended bodies, what happens is the pull or the gravitational pull at this end as compared to this end is very different. So this part is not actually the center of gravity. It's going to be somewhere, let's say over here, essentially speaking. And how do
This
you
is
do that?
in what case, sir, again? Can you say this is in what case? Extended body?
Extended bodies. Yes. So not perfect spheres. So look at this as, a cube, or let's say this soap shaped
All right.
quadrilateral. So in these cases, it's not a sphere, right? It's not uniform in that essence. So the pull of this mass to this mass changes as the distance changes. Okay. So this extended body will have a very different center of gravity. And for that, you need to take help of calculus. You can watch this video if you're interested, but this is out of your syllabus, not in your syllabus. If you want, you can study it, but you need help of advanced calculus. You basically take a small mass over here and integrate it over the entire body to find the center of mass. Not in your syllabus, you don't need to worry about it. But my point was, this point mass approximation is only valid for spheres, perfect spheres, even that. But we can assume it for ununiform spheres as well. Why? Because we're talking about large distances, large separation, right? When we're talking about planets, what's the distance we're talking about? Really big, right? Way bigger than the object itself, that is Earth, or let's say Venus or Mars. The separation we're talking about between two planets is very large. So in that case, point mass approximation, even with non-uniform planets, very valid. Does not have a problem.
All right.
Oh,
So basically, when it's a sphere, we always consider point mass.
hmm, exactly. Whenever it's a sphere, always a point mass. And if the question tells you why can't we consider it to be a point mass in this case, then notice the distance we're talking about. If the distance is very similar to the radius of any object, then your answer should be okay. My separation that I'm talking about, let's say there's a planet M1 over here and planet M2 over here. Now, if the distance is this much, so let's say D, and your radius is R1, then you say, okay, my R1 and separation D is very similar, which is why, which is why I can't make the point mass approximation over here. Uh, Reason being, I mean, by the way, this should be a non-uniform, non-uniform sphere. Only then. For perfect spheres, doesn't matter what D is. Doesn't matter what D is. It's always valid. Point mass approximation for perfect spheres are always valid. But imperfect spheres or non-uniform bodies, for example, Earth, then yes, if your distance is very close to the radius itself, then your point mass approximation may be invalid. This is what I'm telling you. I haven't seen such a question, but I'm just telling you in case the question asks you that. Okay. So in those cases, point mass approximations are not valid. Okay. So extended bodies, you can look into this video. Now, essentially, at the end of the day, I want you guys to understand how to work with the formula or this gravitational force. What is this force again? How to find the gravitational force on any body. So if I give you a small example to how to work with the formula, let's say there are two masses over here in space. This is also our next topic, circular orbits. So, how satellites go around Earth. We can look into that. Now, look at this. Look at this specific part. And I want to just test how you guys can use the gravitational force formula, law of gravitation. So over here, I have a mass M1 and I have a mass M2. Let's give it some number. So let's say this is 30 kg. It's going to be way more than that, but let's just say. And this is 5 kg. By the way, the gravitational constant, if you guys didn't write it down, is 6.67 into 10 to the power minus 11. Okay. Okay. This is the gravitational constant. That is G. That was experimentally found out. Remember, experimentally found out. So this is the gravitational constant. It will be given to you on your paper. So that's great. And the unit of force, what is the unit of force? Newtons. I hope that much we all know. Okay. So even of gravitational force, the unit is going to be Newton. Now coming back to what I was gonna show to you guys is I have two masses in space in a vacuum, and I have these two masses interacting. Fair enough. Now I want to find the force Fg on M1. Let's find that. Okay, let's find that. So the force Fg is going to be 30 kg. So sorry, by the way, G is going to be 6.67 into 10 to the power minus 11. So I'll get that out of the way. So this is your G, gravitational constant, times the product of mass, which is M1, right? What is M1? 30. 30, I've given. And what is M2? So product of mass, both the masses interacting, 5 kg. So G M M divided by separation square. So let me give you the separation as well. Let's say 30 meters. 30 meters. What? Squared. 30 meters squared. Now, go on with the calculation. And what you will see is this force Fg on the big mass will also be the same force on the small mass. You want to find that? Let's find that out. Fg on the small mass is going to be the gravitational force, gravitational constant, sorry, 6.67 into 10 to the power of minus 11 times the force of the small mass that we want to find out, 5 times the other force, sorry, the other mass that we're talking about that it's interacting with, which is the mass M1, which is 30. Divide by what is the separation? 30 meters. So 30 squared. Isn't this the same expression? It's the same thing. It's the same number. So whenever two bodies are interacting, the gravitational fields are interacting all the freaking time, the force exerted on each other is same. This is where Newton's law come in. Pair of forces. Whatever I apply on you, you apply on me. Just different direction. Just the different direction. Nothing else. Literally the same thing. So essentially, this formula is the proof. This is showing you that if this small body applies this massive of a force on this body will also apply the same force on the small body. But the difference is only the smaller body will accelerate towards the bigger one. The bigger one will also accelerate. Logically speaking, yes, the bigger one will also accelerate, but it will just not move as much. Throw a pen from your hand up in the sky and look if Earth goes up or the pen falls down. Which one happens? The pen falls down. So that force that, let's say, the pen applies on Earth, let's say, I don't know how much it's going to be. It's not 5 kg, let's say 0.05 newtons, right? 0.05 newtons, let's say. That amount of force is enough to pull the pen down to the Earth's surface, but it's not enough to pull up the Earth. Sure, both the objects will accelerate and has a force applied on it, but only the pen being so small gets to fall down. Okay, so that's the difference. The difference of size can be seen in the effect of the force, but the force itself is the same. And a lot of people find it very unintuitive. They say, okay, how is it the same force? I remember one of my teacher long back taught business. He was going on, he was trying to prove to me that physics is pseudoscience or something, that physics is wrong. What he did was he took a piece of A4 paper and punctured the pen through the paper, right? So basically toward the paper using the pen, head of the pen. And he told me, look at this. If the same force was applied by the paper on the pen, then the pen should have also fallen down. also broken down. But over here, only the sort of paper tore down. And I was like, no, that's not how it works. That's not how physics works. So, in essence, the force applied both on the paper and the pen was the same. It's just that, it's just that the paper didn't have the structural integrity to hold itself together. It broke. It's not physics' fault. It's just the paper didn't have the strength to hold the force. And the pen did. Pen was strong enough. If the pen was weak, pen would also break. So the force, my friend, is always the same. You can't just go on about breaking laws of physics like that. Okay. So in essence, Fg, no matter what body we're talking about, if both the bodies are interacting with each other, force on both bodies are the same. Okay. If that's clear, we can move on. Now, what are we going to move on to? Hopefully, you understand how to use the formula. Let me write it down for you. The force on any object is going to be given by gravitational constant multiplied by one of the mass times another mass divided by both of their separation, which is r squared. Okay, this is your formula. We're going to work with this very extensively. And we're going to go through some such very interesting proof and derivation. Sure, you may not need a lot of it. Some you will, on the papers as well. They will ask you to derive a lot of these things. I'll talk about what do you say? Gravitational potential energy. Yeah, gravitational potential energy, gravitational potential, astrodynamics. I'm going to show you a lot of proofs. So you will this topic is filled with proofs. And that's why it's also fun because you understand where the formulas are coming from, except for the main formula, which I told you was experimental. Coming back to this topic, 13.2, it is circular orbit, and as I told you, it's basically the best way to imagine this is the satellite going around. Now, this is where again circular motion comes in. I told you guys, circular motion is not a lonely topic. It comes in with multiple other topics. That's how it comes in. So this is one of those topics. So um, think of something. And that is, I remember someone mentioned this to me at some point. It was very interesting. So let's say a satellite, you've heard of the International Space Station, yeah? So what happens there? Why do we have weightless nature in the space station? Why do objects float? I'm telling you guys, if you don't know, objects float in the space station. So if this is my Earth, M1, there's a space station over here, or let's say a satellite, right? I don't know what I'm drawing, but let's just call it a day. That's a satellite somewhere in the sky, and it's orbiting around Earth. And if you step into that space station, it will feel like you're in space. It will feel like you have no force on your body, literally zero. That's how it will feel like. You'll float around inside the space station. But it is near Earth, though, very near Earth. It's not too far away. And if I have a object over here, if I drop it, you know what will happen? It will accelerate towards the center of Earth, and it will fall and crash onto the Earth's surface. So why is this space station not crashing? Why? Why do I feel weightless? Why don't I feel Earth's gravity in the space station, my friend? Do any of you guys have any answer? I'm very interested in knowing if anyone has an answer for that. If I drop any object over here, it definitely falls. It falls down and crashes into Earth. For example, asteroids. But this space station that is orbiting Earth, I step into that space station, I feel weightless. I float around. Why is that? Anyone with any idea? I'm just interested. I'll let you guys, but like, sure. If you guys have any idea, any guess, why do we feel
Maybe because
weightless?
of
Or
orbital
yeah,
speed, like they orbit in a certain velocity because of that.
okay. So, what happens to gravity? Does gravitational
Is
field
it
not
because
reach
there's
there?
no contact force?
I mean, why is there no contact force? Why am I not in contact with the space station? Why am I floating around? So, like someone said, the velocity, sure, but isn't I'm going around with an orbital velocity around Earth? But doesn't Earth's gravity reach here? The gravity is still there, no? The field lines are still here. So why am I not being pulled? Why am I not coming in contact with the floor of the space station? Why is that not happening? Sure, I'm going around with the velocity. But what happened to the gravitational pull that Earth has on the satellite? What happened to that? Why is the satellite not falling down as well? Forget me, the satellite is also not falling. Forget myself, the satellite itself is orbiting around. Is it because it has the same acceleration as Earth? No, then the satellite would have to be very massive for it to have that same acceleration. Then both would have to be. I mean, in that case, what would happen is the Earth would also move towards satellite. If Earth had the same mass as Earth, then Earth will also move towards satellite. Satellite would also come towards the Earth. So, very interesting responses from you guys. Very interesting ones. If any of you guys have anything else to say, I'll listen. And then I'll tell you guys the interesting bit. Why the gravitational field is not working on the satellite. Why is the satellite not falling down? Okay, enough of a brain teaser. Now I'll tell you guys what's happening. Remember in circular motion, when cars were going around and we were saying, where is the centripetal force coming from? Where? What did we say? In case of cars, we said, well, it was friction. The friction provided the centripetal force. What's happening over here? If the satellite is in circular motion, notice the satellite is in circular motion around Earth. So if I just consider this circular mass to be the satellite for now, just assume, just believe me. So this is the satellite, and this goes around in circular motion. Where is that centripetal force coming from? Guess, any guesses? Let me know. In this case, where is the centripetal force coming from?
In what case again?
In the satellite, in case of the satellites going around Earth.
From
So in
the Earth gravity pull, like the pull of the gravity from Earth.
sure, exactly. And what can we call this in this diagram? Which label is it? Like I've written a bunch of names like M2, FG. Which one do you think is the force, centripetal force?
Uh,
The arrow from M2.
Yes, the arrow from M2. Which one? The pink one or yellow one?
Yellow one.
Exactly. So FG over here, this is the gravitational force as mentioned. That is also what we found out. This gravitational force that we found out using what? Gm₁m₁ and this same force, mind you guys, is the same on the Earth and also on the satellite. But as mentioned, this force is not enough to move the Earth. Earth is bloody massive. So this Fg, even though is being applied on the Earth, is not enough to move around the Earth. So you know what moves? The satellite moves. And again, where's the satellite getting the circular motion centripetal force from? This Fg. So this Fg, if this is not circle, but like I'll take this. Basically, I'm trying to draw the orbit. Nope. Nope. Okay, perfect. This, if I change it, please, yeah. Now this is the orbit of the satellite. This is the orbit of the satellite. The white outline that I have. And what is the center? Notice the FG points directly to the center of the orbit. So the center of Earth. The center of Earth over here, we can assume to be the center of the orbit. In reality, if the satellite was a bit bigger, then you would have the center of orbit somewhere around here. Earth would also move around. Earth would also move around this center. But your life doesn't get that complicated. It does for me. I work with that in orbital mechanics. But for you guys over here, you guys don't have to worry about a different center point. If the questions come in, they will always give you such a setup where one of the object is very massive and the other object is very small. And what happens in that case, my friend? The smaller object goes around the bigger object, right? So Keeping that in mind, they will give you guys the question. They will never give you guys a question where the center of orbit changes to, let's say, somewhere in between both the object. That ideally wouldn't really happen for solving the questions. Anyways, coming back to our satellite and Earth scenario, this satellite goes around the Earth in a similar orbit, and that centripetal force that we talked about in circular motion comes from the gravitational force. And the interesting part, or the part you guys need to understand very carefully, is the entirety of Fg, entirety of gravitational force, is being used up by the circular motion, by the orbit. We call it the orbit. And that is why you feel weightless, because that gravitational field is being used up in circular motion, which is why the moment you enter the satellite, you feel weightless, because the gravitational field doesn't exist to act on you. It is already doing the work for centripetal acceleration. So the gravity exists. It's not that the gravity doesn't exist, my friend. It exists. But all it's doing is the work of the centripetal force. It is making sure that your object over here is staying in circular motion. So literally, the gravitational force is working overtime. It has no business with you anymore because it's already doing the work of centripetal force. That is why you feel weightless, because it's already doing the work on the satellite to keep it in orbit. And why do we need the force? Revisit circular motion now. Why do we need the force? Because there's an acceleration towards the center. If you're orbiting around Earth, that means there's an acceleration towards the center. Where do we get that acceleration? We need a force, right? Where is that force coming from? From gravity. From the gravitational field of m1. So the gravitational field of m1 is providing it. That is what's happening. Hence you feel weightless. Hence you feel weightless. But the question is, can I just put an object randomly in the sky and expect it to be in orbit? So let's say I put an object over here, far over here. So I go using some of our rockets, let's say, and I go to the sky from a certain altitude, really high in the space. I drop some random object, a piece of apple, let's say, and what I see is this object won't orbit around Earth. This will go crashing into the Earth's surface. So why is it that the Earth's satellite is orbiting? It's still in the same space, same place. Why is the satellite orbiting but not my apple? Any idea now? Any idea why my apple is not orbiting? Yeah,
Because the satellite had initial tangential velocity and the apple doesn't.
exactly. Accurate. Very accurate. So what happens when you launch a satellite? This is the conversation of what happens when you launch a satellite. So what I as a scientist, or let's say I at the NASA or I at my university's observatory, what I think first thing is, okay, I want to put a satellite in the sky. This is the first mission. Put a satellite in the sky. Second, my question is, where? How high in the sky? My friend, how high in the sky do you want the satellite? And let's say I say 2,000 kilometers. That's how high in the sky I want the satellite to be. Now, this value that I've given now allows me to find out what velocity the satellite needs to be in orbit. So now I find the tangential velocity of satellite. So for the satellite to be 2,000 kilometers away from Earth, high from Earth, it needs a certain tangential velocity. But we don't need to constantly provide that tangential velocity, by the way. So what initially happens when you launch the satellite is it has what do you call it? Thrusters. Yeah, you have thrusters in it, and it accelerates. So we launch it and it accelerates and it goes up in the sky at 2000 kilometers and it starts orbiting. The moment it reaches the certain orbital velocity it needs, the thrusters will fall off and it remains in orbit. So we only give it the initial push. So we have the satellite, we fly it in the sky, we make it accelerate around Earth, right? And we throw off the thrusters. Once that velocity, orbital velocity, we call it, note it down. Once the satellite reaches its orbital velocity, our work is done, my friend. The satellite will go on around Earth on its own. No energy needed, no fuel needed. All you need to do is provide the initial tangential velocity. How do you find the tangential velocity? Do you guys remember circular motion? V is equals to r omega. What is r? 2000 kilometers. What is omega? How frequently I want the Earth to go, how frequently I want the satellite to go around Earth. At what rate of theta? Okay, if you guys remember omega, that is what it means. How much theta I want it to cover every second. That is omega. Even that we decide. Okay, and we will see the maths of it. We will see the maths of it. Don't worry. But in essence, I'm explaining to you guys how the entire thing works. And this is very fascinating. It's very simple, algebraic manipulation of equation. Based on that, we get to put a satellite in the sky. And that's the fun part of this. So look, let's look through the derivation over here. You guys might just like it. So if I have the satellite, right? And what is the force on the satellite? What is the force on the satellite? Fg is equals to Gm₁m by r square. So let's say the capital M is the mass of Earth, small m is the mass of satellite. And the separation is let's say 2000 kilometers. Okay, that's how high the satellite is, let's say. Okay, that's where I want the satellite to be. So now, by the way, just to let you guys know, if the satellite is further away, then what happens with the force? If I increase the separation, what happens with the force on satellite? Decreases. So the further away the mass is, force will decrease, right? So if the satellite is closer to the Earth, force will increase. So if the separation is less, force will increase, inversely proportional by square law. Okay, fair enough. Now, coming back to our topic, what we were discussing, the force on satellite is this. Okay, now in circular motion, what is the formula of force? F is equals to mv square by r. Can I substitute v is equals to r omega over here? Please follow the steps over here, right? R omega r. Can I say mr square omega square divided by r? Can I say mr omega square? Isn't this the formula for centripetal force? This is also, but I'm interested in this. You'll see why I'm interested in this. So this is the formula for centripetal force. And what did I tell you in case of satellite? Who is providing the centripetal force? The entire centripetal force is being provided by gravity, gravitational force. So I say my FC mr omega square is being provided by the centripetal force, is being provided by the gravitational force. That's what I say. Okay, that's what I say. And what happens then? You do a bit of cancellation. So you cancel this with this, and you take the radius, not radius, guys, don't make that mistake, not radius, separation. R is the separation, not radius. This is radius. I've made this mistake sometimes. So this is the radius. Separation is between two objects. Okay, this is the separation. This is what we want in gravitation. R, this is the separation. This is radius. Don't get confused.
Sir, I heard in some scenarios for the separation we take from like the surface to surface. Is that right or no?
No,
It's always
we
center to
never do
center.
that. We never really do that.
So it's
Where
always
did you see that?
center to center, or
Yeah, center to center. Where did you see that?
no? I heard like my teacher was teaching, and then I heard like in some cases. I'm not sure if that was right or not.
I'm
Or
trying to
maybe
imagine if I'm
he
trying to.
meant that
Yeah.
not to take from surface to surface and take from center
Okay.
to maybe that was what he meant.
Okay. Could be. Because I'm trying to imagine if there's any case where I would go surface to surface,
Right.
and not really. That would
Okay.
be wrong. Uh, I mean, it's insignificant is a different question. Some cases when the separation, as mentioned, is very large, it may be insignificant to consider from surface to surface or center to center because the radius is very small as compared to the separation. So the conversation can be that, okay, it's insignificant, but no, it's not going to be accurate. It's always accurate to go with the geometric center of the sphere. Anyways, hopefully that's what your teacher was talking about. Now coming back, um, what was I doing? Yeah, canceling off a bunch of things. So over here now, when I have the separation, right? R is the separation. So when I have the separation, R over here and R square over here, what do? I take it to one side. I take it to left hand side and I call it R cube. So I add the powers. What do? I added the powers. And this, my friend, is still omega, which I broke down. And I'll show how I broke it down. But this is basically the omega. So R cube omega square is equals to Gm. So this Gm is left over as over here. Now, omega you can write it as 2 pi by t. Can you not write this? Circular motion. Recall, guys. Recall. In circular motion, we understood that omega can also be explained as 2 pi by d. So, how much time it takes for an object to go around the entire circle? That is 2 pi radian divided by how much time? So time period. Complete one entire circle. That is 2 pi. So 2 pi divided by time period is omega. Hopefully you guys remember that. If not, just revisit. No worries. So I say 2 pi by t whole square. Or I can say 2 pi whole square because I'm dividing. Sorry. I am distributing the powers in Dyson rule. So I'm distributing the powers to the numerator and the denominator. Okay. So this entire thing is omega and this is the square. Hopefully this part you're not confused about. I'm explaining it way too much, I guess, I feel like. But anyways, so that is your omega square. This is your RQ and this is your GM. Now what do? What we're gonna do is we're gonna make just the R cube the subject. Just R cube the subject. So in doing that, so I take t squared over here and I take 2 pi square over here to the denominator on the right hand side. So if you follow the steps accurately, you will not be confused about which step, which is what I'm interested in. If you follow the steps correctly, this is ultimately what you get. And you will notice 4 pi square and Gm. Is mass not a constant? Is the mass of Earth changing? Absolutely not. Absolutely not. Is gravitational constant changing? No, it's in the name. It's a constant. Is 4 and pi changing? I bloody damn hope it never changes. So none of these are changing. All of these are constants. Okay. So I can consider this to be out of my equation, as in not equation, out of my proportionality, because these are all constants. Okay. When I write a proportionality, what is the proportionality of two variables? Remember that. Constants don't matter in a proportionality. Okay. If I say my sister, forget that, my brother is twice as heavy as me, it is of no substance how heavy my brother is, nor how heavy I am. The proportionality is my brother is twice as heavy as me. So if I'm 20 kg, he's 40 kg. If I'm 30 kg, he's 60 kg. What the number is, how much I weigh and how much he weighs is of no substance. So if I had to say it in terms of equal sign, if I am 30 kg, my brother would be 2x or 2 times 30. So this 2 is the proportionality and 30 is the numbers, the constants, whatever you want to say. Right? So that is how proportionality works. Again, the proportionality If in real life you want an example, my brother is thrice as heavy as me. Okay, that's the proportionality. It doesn't matter how much I weigh, how much he weighs. Numbers don't matter, constants don't matter. Okay. Sorry, why did I underline Kepler's law? That has nothing to do with it. Okay. So the constants don't matter in proportionality. Constants don't matter. So that's why you can say I can omit the constant bit, throw it off, and I say, okay, what I have over here. My time period square is proportional to separation cube. This is a very interesting proportionality we have just found out. And it's very useful as well. Now, how it's useful to you depends on the question that is presented to you. But what this tells you, I'll explain. If I have a satellite going around Earth, E, and a satellite S, if I increase the time period for the satellite to go around Earth, so let's say right now the time period is 24 hours. So let's say every 1 day or in every 24 hours, the satellite completes an orbit around Earth. So it goes around the entire Earth and comes back to the same position. That is what's happening right now. Now, if I increase the time period, my the separation between the Earth and the satellite will increase as a power of cube. So if I want to increase the time period, so if I say, okay, I want the satellite to take 48 hours to go around Earth, then the satellite should be placed where? Way further out. So the altitude of the satellite must increase. If I want the satellite's orbit to take 48 hours or twice as much as a day, then I should put the satellite how far away? How far away? Further than the initial position. And if you want to accurately find out how much, then you use this proportionality. How do you do that? So let's say an example would be if I increase, let's say, the time period by 2 times, so 2 times t whole square divided by r cubed. Okay, so essentially, now it's going to be 4t squared r cube. So your separation, basically, the cube of your separation will be 4 times the initial amount. And if you want to find out the actual separation, then it will be basically for it to be 4 times, I have to calculate. What's the calculator? Wait. Shift of cube 4. Okay, so you need to increase the separation. You need to increase the separation by 1.58 times. That's what you're going to do. Okay. So that's how the proportionalities work. If you have a sum, then I will be able to better show it off to you guys with the numbers. Then you will see how the proportionality really works. But essence, if the time period is increased, my separation will also be increased. And the proportions are in square and cube. And you will be able to calculate that. Okay? You will be able to calculate that. Fair enough? So this is the proportionality and it's called Kepler's law. If I increase the time period, my separation must also increase. Okay. This is what the Kepler's law or Kepler's third law is telling you guys. Yeah, third law. Okay. Any question till this point with the Kepler's law? Try and digest this. You guys have some time. I don't want to be too fast with this because this is a new, completely new thing for you guys. As far as I remember, I don't remember studying anything like this before A2 levels. Now you have IGCSE, space physics. We didn't have space physics in IGCSE, but I don't think anything like this is included there. I don't remember. Okay, take a look at this. Try to digest this. We basically use circular motion idea. I used the formula for centripetal force equated to gravitational force and said, okay, my centripetal force is being provided by the gravitational force. Once I equated that, what did I do? I omitted the constants and I found a proportionality between the separation and the time period. That's what I did. That's all I did. Okay, that is all I did. Any question to this point?
No.
Okay, what do you guys think? This is complicated or easy? I mean, doable. I won't say easy, but like
It's all right.
it's all right. Okay, I hope that's his general consensus around. Yeah. Okay, good. Did we find the proportionality calculation a bit complicated? I would think so. If I just throw a bunch of numbers, then I mean, I would guess that we would find it a bit complicated. But if I show, I don't think I have a question right now. But if you do a paper and you see a proportionality constant, you'll be able to do the calculation and see yourself how the proportionality works between time period and separation. Okay, in AS you must have had enough proportionality questions, real questions in your MCQ paper. I remember having a lot of hard question compilation for those. MCQ used to be pretty decent with ratio questions. Okay, now that's the Kepler's law. You don't have much calculation with it, but the derivation may be important for you guys. This, wherever it's important, I'll tell you guys. Some of the things are made up by me, so I just pulled in from somewhere, and the rest of the things are, I'll tell you guys which are important. This derivation may be important for you guys, not maybe is. You guys should understand this part because it's relating to your circular motion bit, and this will be relevant to you in some questions. Coming back, how to find the speed required to orbit a planet? Right. So the same question we had with the satellite, that how do I make the satellite orbit around Earth? What do I do? What do I do? How do I know the velocity? Sure, I decided it's going to be 2000 kilometers away or up above us. Right. Now, if that's the case, how do I find the orbital velocity or the tangential speed using the same formulas that we have right now? So what we do is we just use a different version of the centripetal force. Up there, we used omega, mr omega square. Why? Because we needed time period in the equation. To figure out Kepler's law, we need time period in the equation. Hence, we worked with mr omega square for centripetal force. Now, we don't need that. We need the orbital velocity. So I somehow need velocity in my equation. Hence, I'm going to use the mv square by r version of the centripetal force. So what I essentially do now is I say that centripetal force is mv square by r. Okay, and the Fc or the centripetal force is being provided by the gravity or the gravitational force. Okay, Fg. So I equate both centripetal force and the gravitational force. Now what happens? Again, a bunch of cancellation. What do you cancel? The small m. Okay, and you make v the subject. How do you do that? You cancel r as well. So v square is essentially going to be Gm divided by r. And now you take a root on either side, right? You take a root over on either side and you're left with root over Gm by r. That looks decent. Okay. So now what do we understand from this equation? This is the orbital velocity. So if I know the mass of the planet we are orbiting, that is, let's say, our own Earth, what happens in that case? We know its mass, which is whatever the mass is, I'm not really sure. That mass times gravitational constant divided by the separation or the altitude I want the satellite at. Mind you, guys, this error I have seen just so much. I find it painful. Like if this is Earth and this is R and this is, let's say, the satellite, and the question gives you the altitude is flipping 100 kilometers. People use 100 kilometers in R. No, no, no. Separation, my friend, separation, not 100 kilometers. 100 plus R, whatever R is. R may be, I don't know, let's say for this case, arbitrary value. Let's say R is 50 kilometers. Point is, or the point I'm trying to make over here is don't just consider this distance to be the R. No, don't. This is altitude, not the altitude. You want the complete separation from the center of Earth. And this is the most common mistake I've seen. Most common mistake in these calculations. Don't do this, please. Please. 100 plus the radius. And the question will trick you with this. 100 plus the radius. Always add the radius when you're doing the calculation over here. Okay? I hope you won't forget. Now, this separation, again, which one? The entire separation from satellite to the center of Earth. Always. That's the R. R. Okay? So, coming back to everything we talked about. If I want the orbital velocity, I need to know the mass of the planet I'm orbiting and the distance I want the satellite to be at from the center of the planet. From the center of the planet, not the surface, not the surface. I don't care what the distance is from the surface. I want it from the center of it. Entire separation. That is R. Okay. Now, one thing to notice over here. One thing to notice over here. The small mass does not matter. Or the mass of satellite does not matter. Does not what? Does not matter. If my satellite's mass is 1 ton or 1,000 ton or 10 grams, if I give it the right orbital velocity, it will bloody orbit around Earth. Does not matter how heavy it is. Look at the equation. And this can be a type of qualitative question to you as well. That doesn't matter how heavy the satellite is. No, does not. If I give it the right orbital velocity, you can bet your money it will orbit around Earth. It's maths. Nothing defies maths. Nothing defies physics. Okay. So as long as you give it an orbital velocity which is equal to the root over gravitational constant times mass of planet divided by the separation, it will work out. Okay. Fair. Now, how to find out the distance of satellite to maintain geostationary orbit? Geostationary orbit. Okay. What is geostationary orbit? We'll talk about that. But one of the properties of a geostationary orbit is it stays exactly on top of one position on Earth. Now, bloody hell, it will be difficult to show on a 2D diagram, but if this is my Earth, E, and this is satellite, then this satellite will always remain above this position. So let's say that's what is an iconic place? I don't know, Eiffel Tower. Okay, so let's say this is the Eiffel Tower, and the satellite, if it's a geostationary orbit, satellite will orbit along with Earth. So as the Earth spins, the satellite will also spin with Earth. How long does Earth take to spin, my friend? I mean, orbit around its own axis, not around the sun. 24 hours. So how long should the geostationary orbit take to orbit around? 24 hours. How long? 24 hours. That's a geostationary orbit. That satellite, it will A be along the equator. B, so this is the equator. I mean, I hope you guys know what the equator is. So yeah, A, it is on top of the equator. B, it stays exactly on top of the Eiffel Tower. I mean, Eiffel Tower or not, doesn't matter. Could be anything, but it stays above exactly one position. If it's your room, then it will stay always on top of your room. So if you launch a geostationary orbit from your room, from your window, then if it's geostationary orbit, the satellite should always remain on top of your room. On top of your room, as in at any altitude, but it shouldn't deviate in the x direction or y direction. I mean, in the x direction. If you can go move left or right, exactly on top of your room, all the time, for the entire 24 hours, again and again and again. Okay, so that's the geostationary orbit. It stays above one position, and its orbit or its period, time period, is exactly 24 hours. So now over here, what do we have? How to find out the distance of satellites to maintain geostationary orbit. What does this question mean? This question means how far up in the sky do I want my satellite to be in for it to maintain a geostationary orbit? Are we getting the point? So I want to find out the separation of the satellite with respect to center of Earth. How far should it be such that it takes exactly 24 hours to orbit around Earth? So it stays in sync with my bedroom. I mean, not my bedroom or anyone's, doesn't matter, but like with one position. So if I have the same orbit, that is, the satellite has the same orbit as me, it does not go out of sync. So I start orbiting along with Earth, satellite also starts orbiting along with me, with Earth. So it takes the same 24 hours. Again, I've repeated that in enough times for you guys to understand, hopefully. So that's the point. That's the entire point of this geostationary orbit. Stays on top of one position. Now, how do I calculate that distance? I know that it should take 24 hours. There's one information I know of the Kepler's law. I don't know the separation. Remember, what's the Kepler's law? E squared is proportional to r cubed. My time period squared is proportional to separation cubed. I have one information in my hand, which is time period. I know it should bloody take 24 hours. Do I know how far in the sky it should be? Nope. Let's figure that out. Okay. Now, we know that this is the formula of the relation of separation and time period, or the Kepler's third law, whatever you want to say. And if I make time period the subject over here, t square, what do we get? This. Hopefully, we all agree on this. This part we can agree. Now, what should the time period be for a geostationary orbit, guys? I hope you guys said 24 hours. I'm gonna move on with that. So if it's 24 hours, again, SI units, convert to SI units. Okay, convert to SI units, and it's going to be 86,400 seconds. Okay, great. So it will stay fixed to a point above Earth. Now, how do I find the separation? To find the separation, you will now make r cubed the subject, which is the separation, and you make that the subject and you put in time period as 86,400 seconds. Massive number. Times 6.67 into 10 to the power minus 11, which is the gravitational constant, times mass of Earth. I should know this, but I mean, I don't have it off the top of my head. But the Earth's mass, whatever it is, and 4 pi square, just put in the calculator. Now, this will give you the cube of the separation. So finally, R will be cube root. Do you guys know how to take a cube root? So shift and cube, sorry, shift and square root. This should give you pop up this cube root. Okay. Other way is, let's say I want to take the cube root of 400. So to the power half 1 by 3. This will also give you the cube root. There's another way to do it. And if some of you guys are wondering what is this calculator, it's called Calculus or something. I don't know. Scientific calculator. I always use this. I literally don't have a calculator around me. It's convenient. Anyways, so this is how you can find it. Okay? This is how you can find it. So coming back, What are we coming back to? Yes. So the separation, how do you find out? T squared times Gm divided by 4 pi square. So this is now your separation. Again, guys, this is not altitude. The question will also trick you in a different way. The question will ask you, okay, what is the altitude? This is not the altitude. This is the separation. So what do? You subtract the radius from this. Whatever the answer you get, subtract the radius minus the radius, and you get the altitude with respect to from the surface of Earth. Okay. So if this is the satellite and the Earth, what you have found out, this is this R. So if they ask you what is the altitude, what is the alt, you say R minus the radius, which is this. Okay. They can ask you this as well. Oh, I'm just saying. I'm just making your life a bit easier. Okay. So that's the distance. Any question at this point? We understand how to find geostationary orbit. What was the condition? 24 hours. That's the only condition. Mathematically, that's the only condition. Qualitatively, there's a gazillion other condition for a geostationary orbit. But mathematically speaking, it just should have an orbit of 24 hours, nothing else. We don't really care about anything else when doing the maths. As long as my orbit is 24 hours, it's a geostationary orbit. And it should be along the equator. Okay? Okay. Hopefully that much is clear. And I can take you to geostationary orbit. And this, I have zero clue how I explain this without a globe. Okay? It's easier to explain with globe. I have explained it without a globe as well, but it's just a bit difficult. What are the properties of a geostationary orbit? Till this point, you have some amount of an idea of a geostationary orbit, right? 24 hours along the equator. That's the geostationary orbit. Okay? Okay. The properties of geostationary orbit, let's read. It remains exactly above, directly above the equator, as mentioned, above a fixed point. This one point, you all know. You have mastered this point by now. Second point. Wait. Second point moves from west to east in the same direction as Earth. So, do we know that the Earth moves from west to east? That's the first question I have. I mean, give me a thumbs up if you guys know that the Earth moves from west to east. Okay. I have one person. Two people. Okay. So wait, so then I'll have to explain what west to east is. So look, with the Earth orbiting, let's do this. Oh my God, how much writing do I have? Okay, blank space. So let's take this Earth. This is Earth, our beautiful Earth. And let's say this is the north, this is the south, west, east. This much, hopefully, we can agree. Okay, this is how the things are, poles are. Okay, this is Earth, Mr. Earth. Now look, I wanna take a bird's eye view. I mean, birds are everywhere on Earth, but like, you get the point. I want the top view. Okay, and now I'm going to draw this top view. I'm going to do what? I'm going to draw this top view. So I'm from the North Pole, I'm looking down on Earth. I'm looking down on Earth from the North Pole. So this is the top view. This is the what? Top view. Top view from the north side of the Earth. So I'm on the north side of Earth in the sky and looking down on Earth. This is the north side of Earth. And this is my, what is this going to be? Okay. Let's say this is west. Okay. and this is east. And there's sun over here somewhere. And so sun should be massive. Anyways. So now what happens is this piece of Earth or rotates west to east. This is what it means. So this turns as it spins around Earth. It goes la 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 like that. Okay. So it just spins around the sun, and as it spins west to east. Are you getting the point? So the western side of the Earth turns towards the eastern side of Earth. A
Could you
question?
show that again, please?
The scribble.
Like, how does it move around?
So like this, it goes orbiting around the sun, right? So this is the direction of the orbit. So it goes from the west side over here, spins. So the Earth orbits about its axis. So this is the axis, runs down through the North Pole, let's say. So in this position, let's say this is where the Eiffel Tower is. I don't know why I'm talking about Eiffel Tower, but this is where the Eiffel Tower is, and it will rotate and it will come towards on the eastern side. This is how the Earth is rotating. Okay. So if it's day on this side at 3 p.m., after 3 hours, is it 3 hours? No. 24 divided by 4, that is 6. So after 6 hours, this position on the west side will turn to this side. Okay, this is how the Earth is orbiting. Okay,
Right,
so as
but
it, yeah,
in the middle, it's going from east to west again, isn't it?
yes, yes.
So what do we mean by it goes from west to east?
So we're talking with respect to the sun over here. Are you getting the point? So in front of the sun, what's happening? The west is coming towards the
Oh,
east.
all right.
Okay. So yeah, and good question though. You made me think about it for a while. But yeah, so the west side is turning around and coming to the east side with respect to the sun. Let me make it easier with that sentence. So essentially, that is what it means to for an object to go from west to east. And what they mean by the orbit should also be west to east. So if the object or the satellite is over here, right, this should also go from west to east. Okay. Okay. Wait, give me 1 minute. Okay. So now, when you have the geostationary orbit, there's one more condition other than the west to east thing. So that is going to be the third point. What this has an orbital period. I will, yeah. So the same thing I discussed up there, we using which we did the calculation that for it to be a geostationary orbit, my satellite should also have the same orbit or time period as 24 hours, right? So if it does not have that, then the satellite will go out of sync with respect to our room, right? So if it takes 30 hours and I take 24 hours to go around Earth, right? If Earth takes 24 hours to spin and the satellite takes bloody 30 hours, then the satellite will be 4 hours behind me. So like it will be behind me in terms of spinning west to east. So I will have in 24 hours, I will have gone around and come back to the same position, but the satellite will be lurking behind somewhere. But it's supposed to be over here. The satellite should be over here for it to be a geostationary orbit. And about right, other thing about the west to east thing. Do you guys know that the sun rises on the east? Yeah. Is that something? Give me a thumbs up. Do you guys know that? Then that will make it easier for you guys to understand the west to east concept. No? You guys don't know that sun rises on the east? Yes. So what? Okay, some people may also be. I was once confused. What does it mean for the sun to rise on the east? So what it means is same logic over here. So if this is my eastern side, okay, if this is my eastern side, and this thing is going around, you know what? I'll put a few marks. So if this is the thing, let's analyze this as a country. Consider this to be the United Kingdom. Okay. So now what happens is I'll mark the eastern side of this country. This is the eastern side. This is the western side. What happens is, where is sun? Let's not change the position of sun. This is my sun. Okay. As the earth rotates west to east, whoa, sun rises on the east. So the sun is basically shining on the eastern side. And now the sun is shining on the entire UK. And whoa, the sun is setting on the west. Is that clear? So the sun is setting on the west and the sun is rising on the east. Again, demonstration. Sun is rising on the east, setting on the west. Okay? That is essentially what's happening. That's another way to look at it. So if the sun is rising on the east, setting on the west, then the earth must be going from the west to east. And which I showed to you guys. The sun is going from the western side to the eastern side. Okay? With respect to the sun being there. Okay? That's how we are. I mean, this is not physics. This is just what do you call it? A way of keeping a measure of the orbit. Oh, sorry, what am I saying? A way to sort of measure how the orbits are working. Not measure, but keep track how the orbits are. So it's a way to understand the direction. Why does north, south, west, east exist? Give us a sense of direction where what is. So in terms of the orbit, when I say it goes from west to east, it just gives me a sense of direction. Which side is the earth turning towards? That is all it is. It is not essentially like some complicated physics or anything. It's just arbitrarily put on. Anyone can call it anything. Okay, someone can call the western side the eastern side, and the eastern side the western side. That's not physics. It's just arbitrarily assigned poles. It doesn't really matter. Okay. So, but we get the point of the West. Give me a thumbs up now. Do we understand what it means to go from the western side to the eastern side? Beautiful. Great. So now we understand what it means to go from the western side to the eastern side. Or why do people say for so long in history that sun rises on the east? We saw the demonstration. That's how it works. That's how it works. Okay. Now, a question from your question paper. A satellite in geostationary orbit appears to remain above the same point on the Earth and has a period of 24 hours. State two other features of a geostationary orbit. What are the two other features? It will remain directly above. It will remain directly above the equator or has an equatorial orbit. This is a word you can learn. Equatorial orbit remains above the equator. By the way, none of you guys asked me this, but why is it necessary to be near the equator? Why is it necessary to be near the equator? So, if I just go ahead and explain, it is only when you're near the equator that you cover you're above, you're getting the entire centripetal force or the gravitational force. I'll explain why I say that. So, if the orbit is not equatorial or somewhere over here, notice the red hemisphere. Notice the red hemisphere. I draw field lines. If I draw field lines, where does the field line go? Inside Earth. And if I have an equatorial orbit over here, where does the field line go? Right along the equator. And notice this. If this is one of my orbit, the red one, then that field line, that gravitational field is not entirely contributing towards the orbit. So I will need to find the cos theta component of the field line or the gravitational field over there. that will be giving the centripetal force. Are you getting the point? This is a bit complicated, my friend. So it's okay if you're scratching your head right now. But what happens in case of, what do you call it? Non-equatorial orbit, which is the red one, is it is since it's up in the north, you know, the field lines around a circle goes like this, right? So it goes like, I wish I could draw this better. So like just make peace with the drawing. So if these are the, you know, field lines, notice around the equator what's happening. Around the equator what's happening, that whenever I have the field lines and this is the orbit, so this is essentially the orbit, then all of the gravitational field gets used towards the centripetal force, right? Gets used towards the centripetal force or centripetal acceleration. Now, when I have an orbit that is like this, non-equatorial, there's a theta over here, my friend. So this, with this field line, there's a theta over here. The entire field line can't be used. The entire field strength can't be used. So the cos theta component, this is a bit more complicated maths. It may come in your syllabus. If I were the teacher, I would just make it up. But essentially, over here, the entire force is not being used because it's a non-equatorial orbit. Over here, this field line is making a theta with the equator. Sorry, with the orbit. What theta? Over here. Okay. So now this component, this cos theta component, is the gravitational force that is being used as a centripetal acceleration. Look at the line of force. This is the line of force. Where is the center of the circle? This. This is the center of the orbit. This is towards what? The centripetal acceleration acts. Okay. So that's why we need an equatorial orbit. Now, can the orbit also be, well, if this is north, if this is south, can the orbit also be, well, this, like, for example, around the diameter over here. So around the diameter. So even though, technically speaking, people won't classify this as a geostationary orbit, reason being it's not along the equator, which is this, which is along the west and east, right? But this is also accurate. This is not wrong. This is not, even in this case, the entire gravitational force, since notice, it is the entire gravitational field line, if I draw radial lines, is pointing towards the center of the orbit. No theta over here. So even this would allow my orbit, my satellite, to get the entire gravitational force as the centripetal force. So if this is my field line, the entire gravitational force gets used up as my centripetal force. Okay. Okay. See, this is all right as well. I mean, this won't be classified as a geostationary orbit. That's a different thing. But in essence, this is all right as well in terms of getting the entire gravitational force. Okay. Technically, this is also along a different equator. I mean, it's not equator, but it's along the diameter of the Earth, which is why it's okay. We get the entire force. Okay. It doesn't matter if Earth is spinning over here. In terms of getting the centripetal force, my conversation is the field line in line with the centripetal acceleration? If it makes a theta with the direction of centripetal acceleration, then we now take a component. As you saw in the cos theta case, we take a component of the gravitational field, which acts in the direction of the centripetal acceleration. Okay. That's a bit extra bit, but hope it helps. So that's it. Oh, the other point is move from west to east. I showed that atrocity of a demonstration. But basically, yeah, the geostationary orbit, the satellite, should go from the west to east. Very simple. Two things. This I have explained before coming to this. So I told you guys that how we use thrusters to, accelerate the satellite to a certain velocity. And once it reaches that orbital velocity at any given distance up above the Earth, then it remains in orbit. Then the thrusters come off and the satellite will remain in orbit. Okay? So that's how it works in practical life. Now, a question. I asked this question to a lot of people. Uh, if I throw a ball, like, I don't know if you guys have played cricket or anything, that's a thing for us. So it's basically a ball. Okay? Take a ball and throw it. And why does this ball not orbit around Earth? Forget friction, sorry, air resistance. Forget there's air resistance. Forget that. Forget there are trees. Forget there are buildings. Why does the ball fall down to Earth? Any answer? Any answer? Why doesn't the cricket ball or the ball in general, when I throw it, orbit around Earth? Forget air friction, air resistance. Forget anything. Yeah.
It needs to have initial tangential velocity to
I'm
orbit
giving
the
the
Earth.
initial. Yeah. So you're telling me it doesn't have the right tangential velocity. Is that what you're telling me? It should have more.
Yes.
Yes. So the problem lies in the velocity or the initial tangential velocity that I provide. It's less. Okay. So if I do the calculation in front of you guys to prove it to you guys, if I, again, I want to find the orbital velocity. So near Earth, let's talk about near Earth. Okay. So I'm saying my mv square by r, or the centripetal force, again, should be equal to the gravitational force. Fair enough. I do the cancellation and I find v is equals to root over g times m, mass of Earth, divided by my separation. Guys, notice, what is 2? Altitude above Earth plus what? Radius. Don't forget about this, please. You can't just have 2 over there and call it a day. No, not gonna work. Okay? So you need to do 2. I mean, 2 over here is insignificant. So even if you don't add the 2, it doesn't really matter. But just for the sake of conversation, I'll add the 2. 2 plus the radius, which was this 6,371. It's an odd way to write insignificant figures. Okay, so 6,371 times 10 to the power 3 is the radius of Earth. Now do the calculation, find the velocity. What is the velocity? 8 kilometers per second. Now, if you have that much strength in your arms and you can throw the ball at 8 kilometers per second, it will go around Earth in orbit. I mean, it's a different thing that we also have air resistance. Okay, so yes, that is also a reason that it will slow down.
So to give it a tangential velocity, we must always throw it sideways.
How else could you, for example, like upwards?
No.
Yeah. So like, I mean, see, you just answered your question. So let's say I have Earth over here, and this is a satellite and goes around. I wanna give the velocity or the thruster velocity in line with the tangential velocity. Okay. So as it goes, how does it go around? Basically, when I shoot out a satellite, it spirals around Earth. Spiral, 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 and then finally, not doesn't it doesn't spiral around Earth. It just starts with 0, goes, increases, 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 and right over there, it finds the orbital velocity and stays in orbit. Okay. It starts seeing that, okay, the gravitational force is providing my centripetal acceleration. So that's how it goes in orbit. And this is the orbit. Okay. So it starts, increases, and the thrusters are providing the thrust, the initial velocity. Okay. It keeps accelerating until it finds the right velocity and the right position. 2 things. What am I doing? Okay. So yes, I give it the right velocity, it will go around. Pretty sure about that. 8 kilometers per second if you want to experiment it. Someone had a very interesting input over here. When I shoot someone, I don't know why he said that, but He said, if I shoot someone, does the bullet go around Earth? And if it has 8 kilometers per second of a speed, pretty sure it will, if it doesn't get slammed by a building or air resistance. But yeah, there you have it. Now there's a different kind of orbit, polar orbit. What is polar orbit? Polar orbit is still across the diameter of the planet. So if this is my north, this is my south. It's still across the diameter of Earth, but it's just not across the equator. So if this is my west and east, okay, this is my west and east. This is equatorial orbit or geostationary orbit, but we're talking about polar orbits. So it's sort of 90 degrees to the rotation of Earth. So if Earth is rotating west to east, pretty much 90 degrees to that, right? So what happens in this case? Now, polar orbits, if we just go through the steps, in essence, I've written it down. This is where the satellite rotates about the axis of both poles. What does that mean? If I have north and south over here, the satellite goes around the axis of both the poles. So it goes around like this, goes around like this. Okay. That is going around the axis of both the poles. Fair. Now, it is not a geostationary, meaning it is not fixed about one position on the ground and does not move along the equator. Isn't that clear to you guys already? Obviously, if my Earth is spinning around west to east and this bloody satellite is going from south to north, obviously I'm not going to stay about the same fixed position. While the west to east goes about this position, Earth is spinning about this position, I'm going up. The Earth is not moving up with me or rotating up with me. So I'm not going to stay above the same position. So that's a problem with polar orbits. I don't stay above the same point. I don't. So that's one. Second is it does not move along the equator, of course, because I'm going from, yeah, polar orbits are unit syllabus. Yes. I used to not teach this. Then I saw a question. CIE syllabus, that I can guarantee. But yeah. What was I saying? Yeah. So it goes from south to north or north to south, doesn't matter. That's a polar orbit. And in case of polar orbit again, one of the key attribute with polar orbit is it can travel in low altitude. Why is that the case? Do we remember the Kepler's law and how we found out the distance at which geostationary orbit should fly? Now, in case of polar orbit, since it's not a geostationary orbit, and we don't need a 24-hour time period, so since the time period is that big, the satellite needs to be really up in the sky. Now, if my time period I can just reduce down, right? I can reduce down the time period. Well, I can have the satellite close to me at lower altitude. That is essentially what happens. So in polar orbit, the benefit is you can have it at lower altitude, near you, near where your research center is, let's say, or observatory is. Observatory. So yeah, when you have it at lower altitude, there are certain benefits. When you have a satellite at lower altitude, there are certain benefits, and I'll talk about those as well. So it travels at lower altitude because I don't have the same 24-hour limit anymore. It can be lower. It can complete the orbit around Earth at a lower time period, no problem whatsoever. Okay, so time period is lower. Now, since the satellite is at yeah, because we don't have we don't need it to yeah.
Yeah, like why is the time period
Why does
smaller?
no? It's not smaller. It's just we don't need it to be 24 hours. So we don't assign a 24-hour time period. So we just say, okay, you can have a time period of 10 hours. Doesn't really matter. So in case that's the benefit with polar orbits, right? So we just assign it a lower time period value, let's say 10 hours or 5 hours. And if the time period is lower, the altitude at which satellites can be in, these satellites can be in, is lower. That's the benefit. That's why we have polar orbits. Okay, fair?
Okay.
Okay. So the time period is lower. Okay. Now, what is the benefit of the satellite being at a lower altitude? The benefit is you can transmit the information very easily. You can do what? You can transmit the information with the satellite very easily. So what happens in that case is when it's closer to you, the information loss, A, is less. B, the amount of time that information takes to go from me to the satellite and again back to me is less. So less lag or less delay in information, less lag. That's why you have lag. That's why you have a delay in response. Okay, so it takes less time to travel. That's why we want a lower altitude. And the benefit with polar orbit is we already have something in the equator. Um, orbits going around the equator, and we don't really want to obstruct that. We don't want to obstruct that, right? So no matter where we put it, higher up in the sky, lower up in the sky, right, it's going to obstruct the satellite, not by sort of going into it, but by just coming under it or going above it. So this with polar orbit, what are we saying? It can have a lower time period, so it will complete the oscillation in less time. Okay, so if it was along the equator, what would happen? If I wanted to complete the orbit in less time, then it would, if I have a satellite already over here fixed to this part of Earth, then if I wait, if I have a satellite fixed to this point on Earth, if I have another satellite now, which I have decreased the time period of, it will go around Earth and come and barge in with this satellite as well. Now, this satellite doesn't move with respect to this position on Earth, but my satellite with a lower time period does. It does not stay sort of fixed with one position on Earth. Because I want this to go around, collect some information of Earth, and come back to me. That's the point of polar orbit. Because I want it to collect information of multiple parts of Earth. I don't want it to be fixed. Are you getting the point? Now, equated geostationary orbit act as a great way to transmit information. Okay, it's really fast, right? It's above one position. So scientists don't need to go and calculate, okay, at flipping 12-hour o'clock, I'm going to have my satellite at that hemisphere. That doesn't need to happen. That is why geostationary orbits are important, because it stays right above the space observatory. And the transfer of information is easy. Now with polar orbit, what happens? Let's say it's collecting weather information about the weather. So it can go around Earth, collect that information, and since it's in low orbit, the transmission of information is easier, is faster. I hope now you understand the relevance of polar and geostationary orbit. Are you getting the point? So that's why we have different orbit. A, it doesn't obstruct the geostationary orbit. B, it's in lower orbit, easier to transmit information and collects image and data from multiple parts of Earth. That's why we have polar orbits. That's why we have different types of orbit. You will also see some awkward orbits like this. We have multiple satellites up in the sky. That's a different thing. But yeah, we try not to annoy the other satellites which are in place and which are very important. Anyways, so yes, in essence, again, when you have at lower altitude, information can be transmitted faster with less data loss. At some point in level physics, you guys had data loss things in your question as well. Data attenuation. I don't know if that's in your syllabus anymore. No, it's not. With your syllabus, it's not. But I don't know if in O level or other curriculums it is. Okay, so that is how it works. Fair enough. Now we have one more thing. This is what. Okay, gravitational field strength. I need to cover this next class. That is easy if you have understood the law of gravitation. Pretty decent. possible. Not gonna be a big of a problem, but I want to go across this question since we have 9 minutes. I guess it's time well spent if I cover this. Now, it's a bit similar to what we just discussed right now, but I just want to discuss a few extra things with you lot. For example, what did I mark with? Wait, this one. So now, let's say if I just read out the question for you lot, what does it say? So there's one advantage and one disadvantage of using geostationary satellites compared with polar orbiting satellites for communication between points on the Earth's surface. If I read too fast, you can take some time and read it. But if I just go on with the question, what is the advantage of having a geostationary orbit? No tracking required. No what? Tracking required, because it's exactly above your fixed position on Earth. So I don't need to keep tracking where my satellite is. No need. It can be anywhere. I mean, it won't be anywhere. It will be exactly above your observatory. So no tracking required. Okay. Now, since the satellite is always above one point on the equator, the orbit of the satellite is the exact same as the Earth orbit. Okay. So that's the advantage. I mean, main advantage is this is the explanation. But main advantage is no tracking required. That's the advantage. Disadvantage, orbits are longer, hence farther from the Earth's surface. Therefore, longer time delay and greater attenuation. What is attenuation? Data loss. So what happens when large distances are being covered? Quality of data deteriorates, decreases, information loss in the process. So the disadvantages, large distances, time delay of the information, and data loss. Now, in case of the extra part, I guess, in case of polar orbit, in case of polar orbit, what happens is the orbits are shorter, hence closer to the surface. Now, can I prove this by my maths? Yes, you can, by the Kepler's law. So if I equate my centripetal force to my gravitational force and I cancel the mass, I get to the Kepler's law. So what I'm essentially saying is when I have orbits closer to Earth, so less r, the time period will also be less. So the orbit will take a shorter time to complete. The satellite will go around Earth and come back to the same position in a shorter period of time. Why? Because it's also closer to Earth. Very simple, right? It's in proportion. In how much proportion? Cube to square proportion. Okay. So this is the proof of how the varying the distance of the orbit varies the orbit of the varies the time period of the orbit. Okay, so that's the thing. There's the thing with polar orbit. And last thing is geostationary orbits are longer, farther from the surface of Earth. It's the same thing. Well, I don't know why I wrote this again. But yeah, geostationary orbits take a longer period of time and covers a greater distance. Now, gravitational field strength, I'll give you guys a bit of a pointer and heads up so I can get into it really fast next class. The thing with gravitational field strength is, do you understand what force is? Gravitational
Sir,
force.
could you go to that
Yeah.
the polar part again? I wanted to take a
Yes.
screenshot so I can note it down later.
Go ahead. Go ahead. Yeah.
All right.
Okay. So now with the gravitational field strength, okay. So the gravitational field strength, I'm going to relate it with force first. How do you explain force on on any object, you can say that the force is essentially Gm₁m by r squared. This is the force, isn't it? And if I have, let's say I'm talking with respect to Earth, this is the mass of Earth, right? So if this is massive Earth, E, and this is object M, small mass in the space. Okay. Now, talking about the same Earth, but different mass of objects. So now I want to talk about small mass M2, big mass M3, three objects I want to talk about. But same Earth, not changing that. So I'm keeping M constant, the Earth. What I'm changing is M, small m. Now, what does your intuition say? Is the force applied on M1, M2, and M3 going to be same or different? If I answer for you guys, it's going to be different. Doesn't matter where they are. Yeah, let's say they're in the same place. I'm telling you guys they're in the same place. But the amount of force exerted on any of these M1, M2, and M3, it's going to be different as compared to each other. Why? Because notice there's a variable called small m, which counts for the mass of the object we are measuring the mass on. Sorry, measuring the force on. So now if I vary the small mass, I also vary the force on the mass. But I just want to know that at this position, which is 200 meters, away from Earth, at this position where all the masses are, small masses are, what is the field strength? What is the per unit mass force applied? So I just want to know with respect to this position, 200 meters, from the Earth's center, anywhere along this radius, what is the force applied on any mass, not any mass, on any 1 kg of mass? I don't care if it's M2, M1, and M3. I'm not talking about masses. I'm talking about just any 1 kg of mass. If I put a 1 kg of mass over here, what's the force on that 1 kg of mass? 1 kg. Now, if I increase the radius and I say, okay, I want to analyze the force on a 1 kg of mass in this position, that is 300 meters. What's the force over here for 1 kg? That is gravitational field strength. On 1 kg of mass, what is the gravitational force? The reason it's important is because it makes a uniform idea of how strong an object's gravitational field across space. So if I extend this orbit into larger and larger orbit, I get to understand on 1 kg of mass, in all of these positions, what is the force being applied? What is the force being applied? And then, if I know the force on 1 kg of mass in any of these positions, I can simply multiply it with any mass, 100 kg, 200 kg, 1000 kg, and I can get the force on those masses as well. So to uniformize everything, what we do is we understand the force on 1 kg of object. And that is called the gravitational field strength. At any given position, what is the force on a 1 kg object due to a massive mass at the center? Or anywhere, the center or not, it doesn't matter, but like I'm just saying, wherever they are, what is the force exerted by this mass on just the 1 kg of mass? And that force will change based on the distance. As you go further away, force decreases. If it's here, force is less. If it's here, force is more. And that, my friend, is the small introduction to gravitational field strength. I hope I could explain the three chapters in this class well enough. And tomorrow, please be there because we're going to pretty much complete gravitational field strength. Okay, we're pretty much done. Any question, you can go ahead and ask me. Otherwise, you're free to leave for the day. So we're done with the class. Okay, any question, you can go ahead and ask me.
I had a question on the polar orbits.
Yeah, go ahead.
Why is the altitude lower for polar orbits? Like, can't we adjust geostationary orbits also a bit lower?
No, then you're not going to get 24 hours for geostationary orbit. So
See,
it will,
it has to be at a certain altitude for it
yes,
for it to be
that's what we
geostationary.
find out. Yeah, so like when we did this calculation, if you see, we put in 24 hours, so 86,400 seconds, and we found out if if my orbit is not specifically above this distance. So if I r cube root of 86,400 second times 6.67 into 10 to the power minus 11 times mass of Earth, whatever it is, divided by 4 pi square. So whatever value you get over here, let's say it is 2 into 10 to the power 5 kilometers. I don't know, I'm just guessing it. This is the not altitude, the distance from the center of Earth that the satellite should be in for it to be a geostationary orbit, because it needs exactly 24 hours of orbit time. So it stays right on top of the observatory, let's say. Okay. So now there's a limit or there's a specific distance r at which the satellite can be in. So there's a specific distance and there's a specific time period, which is why geostationary orbits are not flexible. Polar orbits are. And you can say that, okay, along the equator, why not just not have a geostationary orbit, but along the equator? So what happens is, as there is a geostationary orbit, another satellite will go below it because I've reduced the time period. So now the other satellite goes around the equator, but it obstructs the satellite on top of it. Let's say the geostationary orbit, because the geostationary orbit does not move around, it stays stuck from with respect to one position on Earth. But the one with the lower time period will move around Earth. So it will obstruct my geostationary orbit. So isn't it rather better to have a polar orbit, which will not really obstruct my satellite? Okay. So that's a better thing to do, I would say. Plus, you can just adjust the altitude to be whichever you prefer, right? So it can cover multiple images around Earth and give you the weather information. That's how weather information is collected, in essence. Okay.
Okay.
Any other question? Yeah.
No other question.
Okay. Perfect. Any other question? Anyone else? Nope. So can we end the class for today? Yep. All right. See you
Yes.
guys. Yep. Thank you,
Okay.
everyone.
Thank you, sir.
See you guys tomorrow. Bye bye.